Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this session. We were discussing about the oscillators in the previous session, and we looked at a simple common source amplifier based ring oscillator. So, you had R and C at the output load like this. You had this R and this is C connected to VDD, and we had these three of these connected like this, and we also worked out the conditions under which such a circuit is going to have sustained oscillations. Okay. So, what we did, we connected it like this, and it is connected in ring in this manner. Okay. So, this particular oscillator we worked out, and the frequency of oscillation f oscillation was equal to root 3 times omega p, if you recall, and omega p was nothing but 1 over r c. So, this was the frequency of oscillation, and we also told you will have the sustained oscillations if the DC gain of each stage was equal to 2. Okay. So, given that the DC gain of each stage is equal to 2, and you will have sustained oscillations here. Now, with this simple oscillator, if you look at it, what all things do we need in any given oscillator, whether this oscillator meet our demands or not. So, the performance parameters, oscillator performance matrix, we have to define that. Okay. Performance matrix, whether this oscillator is good or not, it will meet our demand or not, that is something which we need to figure out. So, first thing is, in this particular oscillator, what is the amplitude of oscillation? Amplitude and frequency stability are the two things which you will measure for any given oscillator. Okay. So, here in this particular oscillator, we made sure that there is a certain small signal model of each block, and the small signal model of each block was something like this, where you have the current source effectively, your load resistor, your load capacitor, and so on, and this was the gate input. Okay. So, if this is input V in, we have this as V out. This was the small signal model of the transistor. So, the small signal model of the transistor which we were using, because the transistor is a nonlinear device. So, our assumption was transistor is in saturation region. This was our assumption, saturation region throughout the oscillations. So, even when you have some swing at the input and output nodes, the transistor remains in saturation region, and the linear gain is maintained throughout oscillations. Okay. Now, you can ask a question that what will be the output swing? Well, the oscillation itself analysis using the Barkhausen criterion did not impose any kind of amplitude limit on this particular oscillator. So, you can say that you are going to have swing, the swing can be 1 millivolt also, or the swing can be 100 millivolts also, till the time your these two conditions are satisfied. Transistor is in saturation region and our linear gain approximation is valid. If our linear gain approximation is not valid, we cannot write the gain of this and find the oscillation frequency like this. So, overall we can say the oscillator output amplitude is not fixed, it actually depends on the it depends on what kind of signal you have initially, and you can maintain the transistor in linear using a linear gain model. When we talk about the frequency of this oscillator, this is frequency f oscillator here is root 3 by RC, which is actually depending on the resistor and the capacitor. Okay. So, as long as we maintain these resistor and capacitor values, the frequency of the oscillator is fixed. Okay, it is not going to vary. So, if you maintain R and C fixed and you maintain your DC gain of each stage as 2, the frequency will not vary, but what the amplitude is going to be, that is not fixed, because it depends on how much overdrive you have biased the transistor, what kind of signal swing you are having at the in the beginning when the oscillations build up. Okay. Then the next parameter which we have to look for this oscillator is the tuning range of the oscillator, frequency tuning range, because we are going to use this oscillator in the PLL. So, we should be able to vary the frequency of the oscillator. Okay. So, here well, speaking about this oscillator, you can say if I can vary R and C of the oscillator, I can vary the output frequency of the oscillator. So, varying R and varying C will give you the tuning range for the oscillator. Now, whether you are going to get a linear tuning range or a non-linear tuning range, it depends on how you are varying the resistor and the capacitor. So, what we are looking at is the following, that with respect to your output frequency, with respect to your control, now this can be V control or I control, voltage or current control. Ideally, we want a linear relationship, but you may see, depending on how you are controlling, you may see a non-linear or some other kind of relationship between the control voltage or current and the output frequency. Now, any non-linearity in frequency tuning, will lead to nonlinear PLL dynamics. Okay. So, which is not desired. So, if you change your KVCO, your loop gain, bandwidth and other things will change. So, that is something which is not desirable. The third thing which we would like to know, we will go about with this amplitude and frequency tuning about this particular oscillator, how we can do it in a while. But the other metrics which we are interested is in the phase noise or jitter output for the oscillator, phase noise or jitter performance. Okay. Ideally, we would like to have minimum phase noise, minimum phase noise with minimum power. that is the goal always, but there will be some limits with what you can do in a given process. Then the other thing is power supply rejection ratio. Okay, and this is measured as how you are affecting the VCO output frequency or VCO phase noise with respect to the supply noise. This is called PSRR. Let me just write it with all capital, power supply rejection ratio. This is critical in ASICs where you are having multiple PLLs. Okay, so if each PLL start picking up the noise from the nearby signals, then the output of the PLL will be noisy, not because of the thermal noise in the PLL, but because of the noise coupled on the supply from nearby signals. Okay. So, these are the performance metrics which we will look at during the design of the oscillator. So, let us come to this amplitude and frequency for the oscillator. Okay. So, amplitude and frequency for oscillator. Okay. So, in the example which we have seen, our each cell is actually, if you look at it, when the input changes or you have any swing at the input, the corresponding output also varies, and this the current does not remain constant in this transistor, or you can say the main transistor for this stage for the delay from input to the output, and the outputs, the swing which you are going to get is not fixed. As we have seen, the transistor should remain in saturation region for linear gain model, and the swing is going to be very limited and which is not in your control. Okay. So, if we would like to control the output swing, we would like to have a fixed current going through the resistor. Okay. So, fixed current, because the swing which you are producing at the output, when you have a maximum swing here, right, that time you are actually having a maximum resistance, maximum current going through the resistance. So, if we can control the current in the RC load, then we can control the output swing. So, as an example, let us look at a simple circuit like this, where you have a differential pair as the input and with a fixed current IB. This current can also be, this current is realized with the MOSFET, but this current is fixed here, IB. Okay, you have the load resistance R connected to a supply VDD, and there is a capacitive load connected on both the sides. Okay. This is IP and this is IN, this is VOP and this is VON. Now, this as such as a single delay cell in our oscillator, if we are going to use this, let us look at this operation. So, I am trying to show you with a single cell. This is normally an amplifier sign. So, this block is there here. Okay. You have positive, negative. So, this is actually positive and this is negative, right. So, here I have this as a single cell, and this cell is connect. In place of using a single ended circuit, we use a differential circuit, and it helps in limiting the output swing or defining the output swing as we desire. Okay. So, let us look at it. Fine. Okay. So, now we connect these, right. So, what you have is, so every sign which you are seeing is inversion. So, I can very well connected like this. Okay, it will make an oscillator. So, what I have done is I have created a single, I just created, you can say, first just a mirror image of this which you are seeing here, and then fix the current source which is supplying the current to the cell. Now, for each cell, if you look at IP and IN, and you have a fixed current IB. For this circuit, the gain of this circuit VOP of S minus VON of S divided by IP of S minus IN of S. This is like from differential input to differential output. This can be written as GM times R out divided by 1 plus S R out into CL. Okay. Here also both the transistors are in saturation region. So, what happens here is the small signal model of the circuit which you are seeing on the top. This is, by the way, the gain of single cell. So, for a small signal model you can connect it like this. The current source is ideal and you have, so this node is not connected and you have load R here with capacitor connected to ground. Okay. Now, if there is any GDS of the transistor, the GDS will also come in. Okay, this is ground, this is ground. So, this is R, CL, R, CL. You have GM and GDS, right, and corresponding IP and IN you are going to have at the input. Okay. So, what I have here is this is with respect to the source. So, the source is connected here, this is IP and similarly you have IN. Okay. So, for the given small signal model you will get a gain term like this. Now, the way we have worked out a frequency of common source amplifier connected in an oscillator configuration, in same way we can work this out. So, this is nothing but DC gain into 1 plus S by omega p. As we worked out previously, the frequency of the oscillation will be equal to your root 3 times omega p. Okay. Now, we started this because we want to understand that how we are going to get a desired swing. So, now look at the circuit, and when we are going to have a positive swing here, and this is in a differential connection, and a negative swing here, right. So, this swing is applied at a given common mode voltage. So, you can very well say that I am going to have, so what I am going to have here is, you can say the signal which you are having is VCM plus IP plus VCM here, and if the input is differential, then VCM plus IP can be VCM plus delta V, and this can be VCM minus delta V. So, when you have when delta V is equal to 0, at that time the current which is flowing in each branch is actually IB by 2. Okay. And then when you have a positive swing here, the current in the left branch is more than the current in the right branch, and at one particular time what will happen is, when the swing is maximum and here the swing is minimum, all the current will get shifted to the left branch. So, you can say at any given time, so when the current in the left branch is maximum, then you will have the value at VON as minimum and VOP as maximum. Okay. So, when current in left branch is maximum, right, then you have VON as VDD minus IB times R, okay, and VOP at that time, because there is no current in the right branch, so that is equal to VDD. Okay. So, the swing you are looking at differential swing. So, differential swing is VOP minus VON is going to be IB times R. Okay. So, when you connect these cells in the feedback as shown, what you are going to see the signals during the oscillation phase, or during the oscillation you are going to see swings like this, and I can just assume that these are sinusoids. Okay. The maximum value at any given time, so let us say I call this VOP and the VON, the maximum value is VDD and the minimum value is VDD minus I naught times R, IB times R, sorry. Okay. So, that is the maximum, that is the output swing. So, if we want to control the output swing using such a differential cell, okay, actually gives you the swing which you want, and you can also control the swing by controlling the current IB, right. So, now what we have done is we have actually output swing, I can write it like this, that the output swing in our oscillator V swing is equal to IB times R. Okay. And we also know that the frequency of oscillation is equal to 1 by RC, or root 3 by RC. Okay. Now, this is a problem that your output swing also depends on R and output frequency also depends on R. Okay. So, let us say you design the oscillator at only one particular frequency. At that time, depending on IB, you get the, depending on the resistor, you can always choose IB such that you get the desired swing. But when you would like to vary the frequency of the oscillator, right, in that particular case, while varying the frequency of the oscillator using resistor, your output swing will also vary, which is not a good thing. And on top of that, what is happening is, as you want to increase the frequency of the oscillator by reducing R, your output swing drops, which is like at higher frequency your output swing is lesser, which is, first thing is output swing should not vary with the amplitude, should not vary with the frequency, and second thing is, on top of that, if output swing reduces with the higher frequency, that makes the situation worse. Okay. So, so the thing which we need to figure out at first, how we are going to change the frequency of the oscillator by varying resistor. How are we going to vary the resistor? So, if I just say to tune the tuning frequency in the oscillator by varying, you have two options. Okay. So, let us look at both the options. First one is, I will just first have vary capacitor. Okay. This particular technique is used to vary the output frequency, but quite often the capacitor bank is used to vary the frequency, and capacitor bank means that you are having multiple capacitors connected with switches, okay, and you switch in these capacitors depending on the frequency which you want between your output nodes. Okay. So, if I say at each output node VOP and VON, you had such kind of capacitor banks, you can switch the values. So, you can have C naught delta C and something as 2 power, and binary capacitor bank you can have 2 power n minus 1 times delta C. The problem with this capacitor bank based approach is that the change in the frequency step is discrete. Okay. So, when you are varying the frequency using the capacitor bank, you have discrete frequency step, which is something which is not desirable. You want something continuous quite often, frequency step. Okay. And if you want to have a very fine resolution of frequency step, that capacitor which you can switch in will be very, very small, okay, which actually becomes an implementation problem. The other method is to use a varactor, okay, where you vary the capacitor with some voltage. Okay. So, you can do that, but the range which is offered by varactors in case of frequency change is quite limited. So, both these options are available. This is, you can say, more of a voltage controlled capacitor. I am not saying you can't do it, but the range is normally limited. Okay. This can be done. Second thing is you vary resistor. So, when you would like to vary the resistor, the one way, as we have seen, the way you have used the capacitor bank, in a similar way you can use a resistor bank, but then also you will run into this discrete frequency step. So, what I would like to do is I would like to use a voltage controlled resistor, and a MOSFET is a perfect voltage controlled resistor which we have seen. So, given a MOSFET, it can actually mimic a resistor between the two nodes depending on the voltages. So, let us say this is A and B, this is what you have, this is resistor which you want to mimic. I will use a control voltage to get the desired value. So, how we find the MOSFET, MOSFET for a given resistor? Well, if you have a current ISD, this is PMOS flowing through a MOSFET, then ISD is equal to mu p times Cox W by L V A minus V control minus mod VTP times VAB minus VAB square by 2. This is the current flowing through the MOSFET. So, during operating point you can have you can say a DC or a resistance, equivalent resistance for this particular MOSFET is VAB divided by ISD, which is mu p Cox W by L, okay, into VA minus V control minus mod VTP minus VAB by 2. So, you see that this resistance is actually depending on the VAB value also. It is not an ideal resistance, it is depends on VAB. So, under the approximation, okay, under approximation that VAB is much smaller than, you can say, VA minus V control minus mod VTP, which is also the condition for the MOSFET to operate in linear region. Okay. We can say that VAB by ISD is approximately equal to 1 divided by mu p Cox W by L into VDD VA minus V control minus VT P. Okay. And when this particular MOSFET is used in our current cell, and where was our current cell? Our current cell was, I am replacing the resistor with PMOS controlled by V control with input pair NMOS input pair with a fixed bias current IB. So, this is your IP and IN, VOP, VON, and this is V control. Here you have VDD. Okay. So, for this case, you have, if the resistance is actually equal to 1 divided by, or equivalent resistance, let me just write it, is mu p Cox W by L into VDD minus V control minus mod VT. Okay. So, what you see here is that I have a resistance which is controlled by the gate voltage V control. Well, the way you are seeing right now is it is inversely proportional to minus V control. So, if you increase V control, your denominator will reduce and resistance will increase. So, now the frequency of oscillation, which was root 3 by omega root 3 by RC. So, well, you will get here, and is 1 over R. So, what you are going to get is mu p Cox W by L, okay, into VDD minus V control minus mod VTP. Okay. So, by replacing your resistor with a MOSFET, you can actually control the output frequency. So, I can write it as this is proportional to minus V control, right. And under the approximation, which this approximation is valid, that you need to have you need to have a limit on the control voltage, so that you can use the transistor in linear region. So, now let us see that what is that limit. So, first thing is F oscillator is proportional to minus V control. This is good thing that you can vary the control voltage and you can vary the output frequency. Okay. The other thing is you have a limit, and the limit says that VSD minus VSD is your V out, okay, whatever the output potential, whether this is VOP or VON, right. This is less than equal to, for linear region, VSG, which is V control minus mod VT P, which you, if you just solve this inequality, what you get is that V out is, so the transistor has to be in linear region, which is VSG minus, there is any this is VSG minus mod VTP, okay, and what we have done is VSD. So, when your gate overdrive is larger than your drain to source, source to drain voltage, at that time you are going to have this. So, what you get from here is that VDD minus V out is less than equal to VDD minus V control minus mod VTP, which means that V out has to be greater than equal to your V control plus mod VTP. Okay. Now, this is important, that you see V out, I wrote V out as V out is same as VOP or VON. So, here you come back here and you see that there is a lower limit, there is a lower limit on VOP and VON as per our condition here, right. And what happens when we have a swing? one of the nodes goes to VDD and the other node swings down, which means whatever is the lower limit on your VOP and VON, that is going to limit your output swing. So, this particular voltage appears to be our output limit for our output swing. Okay. So, I can just write output swing V out, which is equal to VOP minus VON at any given time is less than equal to V control plus mod VT P. So, your output swing cannot be anything greater than that. There is a limit, but surely that is depending on your bias voltage, you can always have that, because we also know that this output swing is nothing but VDD minus IB times R on. It is not that you can have only one value of the bias voltage, but you can have one value of the bias current, but you can have a range of bias current as desired. Okay. So, V control controls the output frequency, V control limits the output swing. Okay. So, if I just need to write it, V control also limits output swing. Now, come back to the problem that our output swing, which was IB times R earlier, right, and R becomes a function of frequency. So, our swing is actually a function of frequency. That problem is not yet resolved, because even if I take this is just an upper limit, but output swing is a function of R and output frequency is also a function of R. Okay. So, we will address this problem in a moment. So, if we look at it, our oscillator, we will look only at one particular cell of our oscillator. So, what we have here is that V control controls the output resistor and thereby controlling the output frequency, right. So, what we need to do is, if we want to have our output swing is VDD minus IB times R. This is what we have. So, if our R varies for the frequency, we have to vary IB in opposite direction. So, if R increases to reduce the frequency, then we should reduce IB such that the output swing remains fixed. So, what we are going to do is that the control voltage, we want to fix the output swing. So, what we will do is that the control voltage which we want to have is generated in such a manner that the current is as desired. So, this is our MOS transistor for the resistance. Let me just name also this. So, this is MN1, this is MN2, MP1 and MP2. Okay. So, here if I want to keep the fixed output swing, what I am going to do is I will give this as a reference voltage, right, and control the you can say VR, just a minute, this is, let us say, Vx, and this is our. So, what we are going to do is that this load resistor, we are going to decide the load resistor gate voltage in such a way that the current through the load resistor, okay, and the load resistance value itself, that product remains fixed. Okay. That is what we want to do. that if the resistance increases, IB reduces, such that IB times R remains same. So, think about it, that you just took a copy of this PMOS transistor here, right, and you generated the gate voltage in such a way that if I have, just as an example, if I have, let us say, IB current here, then this voltage, because this PMOS is in feedback, this IB current, this voltage will always be equal to Vref, right. If I increase my IB current, then what will happen? If I increase my IB current, my Vx potential will drop, but Vref will become same. So, what I am doing is, if my IB increases, I actually reduce the effective resistance value of this PMOS. That is how we can get the gate voltage of the MOSFET transistor, MOSFET, which is used as a resistor. So, we will use this particular logic with our cell, a replica of the cell. So, the top transistor is a replica of MP1. So, I will write MP1 dash. This transistor is a replica of MN1, so MN1 dash, and then you have a current source. So, in place of current source, I am replacing with the current source transistor with bias VB. And other thing is, when will all the current shift to one of the branches? When either of these potentials in our case will go to VDD. So, I am going to connect this to VDD. Okay. Now, if there is a current IB here, right, for IB current, I will get the resistance value, equivalent resistance value for this transistor MP, such that this voltage remains Vref, right. So, I can also write here that effective resistance value for this is VDD minus Vref by IB, or if you want to say it the other way, that VDD minus Vref is always equal to IB times R, right. And what we are going to do? We are going to pass this Vx voltage, the Vx voltage which you are seeing here, this voltage is passed as a gate voltage to our load resistors in the actual cell. To all the cells we will give that. Okay. And here you can have the same NMOS transistor to control the bias current. Okay. So, you can do this. Now, you can ask a question, well, what I have done is, I have actually fixed the resistance value, or I decide now the resistance value on this in this delay cell in my oscillator, such that the bias current times the resistance remains fixed. So, my amplitude or swing is, output swing is fixed, but how do I control my how am I going to control this frequency? Well, frequency control you can do by changing this from bias voltage as, you can say, bias voltage plus some V control. This is fixed part, you can say, and this is varying part. So, overall if you want to write it, you can say, yes, this is like V control dash. So, by varying the gate voltage here, right, I am going to vary the current in this, and as I vary the current in this, the resistance will vary, and as the resistance varies, then my output swing, my output frequency will also vary. So, let us just look at that relation. So, I will write IB as some I naught plus GM for this particular transistor, a bottom one. So, I will write this as Mn0, this is Mn0 dash, GM times V control, right, which implies that resistance is equal to VDD minus Vref. Vref is external voltage which you gave, VDD is fixed, Vref is fixed, divide by IB, right. Frequency of oscillation is proportional to 1 over RC, which is 1 over RC. Now, C will remain here, R is nothing but IB divided by VDD minus Vref. You have VDD minus Vref as fixed, right, and IB is nothing but I naught plus GM times V control. So, it is not a problem whether F oscillator is proportional to minus V control or plus V control, that is only going to change the sign, but here the thing is that all these terms which you are seeing here, 1 over C, VDD and Vref, I naught, all these terms are constant. There is only one variable term for the frequency, okay. And your output swing is equal to your IB times R naught, IB times R here, right, and IB times R is fixed, VDD minus Vref. So, now you have an oscillator whose output swing does not vary with the output frequency, okay, and you can vary the output frequency by applying a control voltage here, right. Now, well, when you are going to design with the transistors like this, you will see that this transistor Mn0, the nonlinearity of this transistor will affect your frequency gain with respect to the control voltage. So, if that is the case, what you can do is the following. You want to have the change in the current linearly related to the control voltage rather than using GM, because GM will depend on the control voltage itself. That is the nonlinearity which we are talking about. So, if that is the case, what we can do is we can linearize our current gain from V control using source degeneration. And how we do it? Well, we can have an extra poly resistor or an extra resistor here. Let us call this as R external for a while, and you have a PMOS, and yeah, you can have a PMOS with a diode connected NMOS at the bottom. Okay. So, now here you give V control. So, what happens is when you change V control with the delta V control here, because it is a source follower with respect to PMOS. So, you get roughly delta V control, approximately delta V control change at the output node. With respect to that, the change in the current delta I is going to be delta V control by R external, right, and this changed current value gets replicated in the changed bias current here delta IB, and for the changed bias current you have a change in the resistance value and you change the output frequency. So, this is still connected, this connection still remains the same. So, what we have achieved in our configuration is output swing is fixed, at VDD minus Vref, okay, and output frequency is directly proportional to V control, right, as we have or you can call this as delta V control, right, and yeah, and you can have frequency. This is nothing but output frequency proportional delta V control is frequency tuning. So, depending on how much control voltage you are using or what control voltage you use, based on that you can change the output frequency. Okay. Thank you.